Hello there, welcome back to our channel. And today's session is about design of an audio amplifier using a common emitter mode of a BJT. So we have covered one tutorial video about the common emitter mode of a transistor BJT, and we in that case we understood the equations for the DC analysis of the transistor. And if you might want to recall, this was that circuit where we explained you uh, this circuit is to be used as an amplifier and how we derive various equations. So please refer to that, because after referring to that only, you can come back to this video to see how we are going to actually select the values for the components and the devices, which is transistor. And then you can also see how to simulate this circuit. So let's say you are an electronic designer and you are given such design problem, like you want to design a common emitter amplifier using this transistor 2N3904 that should meet the following specification. Your circuit should deliver 2 milliampere to the load, which is the collector current of a transistor. You are given a VCC about 30 volts. So this V plus right here is 30 volt. You are asked to design an amplifier without a load. The gain should be about -50. Remember, the minus sign comes because it's gonna be an inverting amplifier. You apply a sinusoidal input, you have a sinusoidal amplified output, but the phase would be 180-degree phase. The output will have a 180-degree phase shift with respect to input, and that's why it's a negative sign there. So 50 should be the gain. Output should be 50 times larger than the input. Now you have the input resistance of the circuit. Input resistance of the circuit is what you look from here. That is Rin, and it has a DC value at DC at low frequency. It has a value of 4K. And then your load is given about 1K. This is 1 kilo ohm. And you apply a sinusoidal input, which has a peak value of 10 millivolt at a frequency of 10 kilohertz. So this is your design specs. And with that, you are required to design the amplifier, which will provide you a swing at the output. So let us try to do that one by one. So what you see here, so to understand the DC behavior of this circuit, first I will need to analyze the circuit in this fashion by removing this coupling capacitors, and also there is one capacitor here is called as bypass capacitor. Okay. And I will also remove the signal source, and after doing this, I will produce a DC equivalent circuit as shown right here. And then I will apply a Thevenin's theorem and Kirchhoff's voltage law to get my design equations and obtain the values for all the components. So let me clear this drawing right here. So we know that the voltage gain without the emitter degeneration resistor right here is given as minus GM times RC without it. And we know that as in previous discussion, we've seen that the gain is primarily set by the value of the resistor RC. GM is the transconductance of an amplifier, which is IC over VBE. Okay, and if you recall from the previous discussion, we had we can obtain the value of GM as well. So let me show you that. So this is basically a small signal current. Oh, let me just clear that right here. Just a minute. Right, so here is your small IC actually. Let us write that properly so that you understand better. So here is your small IC divided by small VB, and it is having a value of IC over VT, where IC is the DC value of a collector current and VT is the thermal voltage, which is 25 millivolt at room temperature. So you can get this value of G1. But the problem with the common emitter circuit without this emitter resistor RE, for which the gain is minus GM times RC, is that the GM is prone to the variations in the DC biasing and the temperature and other second order effect. For example, if your DC value of IC changes, you have the GM change, and you have a temperature change, then transistor parameters change and the GM change. Therefore, the RE is added to the circuit, where the circuit is then called as common emitter with the emitter degeneration. It somehow reduces the gain. However, the new expression for the gain is minus RC over RE, approximate. So instead of setting the value of gain with minus GM time RC, now a pure just mere a ratio of resistors are used to set the gain of this circuit, which is what is shown right here. And RE is usually used to set the value of it. So this provides a relatively stable circuit, this adjustment, and output voltage VO, let's say this is your VO, is given as VCC. This is your V plus, or call it VCC, or rather just call it V plus. V plus minus IC times RC. So you have the value of IC, that is 2 milliampere, that is given by the specification, and VCC is also 30 volts. We can actually get the values for the resistor RC. So we know that VCC is 30 volts, IC is 2 milliampere, and let's say we want the VO to be VCC over 2, which is about 15 volts, so that if we have the output voltage, the DC level of the output voltage is about, let's say this is 15 volts, then we can have this output range from, this is 30 volt, so 15 volt up, and this is, let's say, 0, so 15 volt down. So full 30 volt peak to peak output range can be obtained. Now with that arrangement, we can have the value of RC is given as VCC minus VO divided by IC. Okay, so plug in the values. That will be 30 minus 15 divided by 2 milliampere, which is 15 divided by 2 milliampere, which is about 7.5 K. So RC, the value of RC can be set to be 7.5 K. Okay, so the first value has been obtained. So how about I just go to the design circuit to set the value for that circuit. So here is my circuit. So I will just clean the drawing here, and I have this circuit where the RC is right here. So what I'll do, I will right click this component, and then I will set the value of the resistor right there. So let me do that. Just right click and write here 7.5K. That's it. Now, before moving further, let me show you the QN transistor. We need to understand the load line of this transistor. What is load line? Is the basically the characteristics between output current IC and the VCE that helps us to set up and understand the Q point, quiescent point of the transistor. So before that, I have chosen the transistor which is shown here. It has a maximum voltage across collector to emitter about 30 volt, and maximum collector current it can handle is about 800 milliamps. And then if I click here, I remember that the beta of the transistor, we have made one tutorial on this also. So the beta of this transistor is 200. Remember that. Okay, so we'll get the value of beta through which we can actually compute the other parameters. So in a moment, I'm going to show you that. So coming back to our circuit, we got the value of RC now. So that is the first component we have done. Now we move to another slide here where we want to understand the value of RE. So remember, I just said for a common emitter circuit with the emitter degeneration resistor, the gain will be the ratio of two resistor minus RC over RE. So RE was chosen just before a minute, and now RE is generally 10% of the RC. So I will choose that value, the 10% of the RC. So here I go. I have the RE. RC is 7.5K. So it would be 10% of that will be, let's say, 750 ohm. So the RE has been chosen here. Now I come back to the circuit here. Now I want to obtain the values of other components. For example, the voltage at the I haven't shown the two resistors here before. These two resistor R1 and R2 hasn't shown here. So what I have done is RC is chosen, RE is chosen, and before that I want to get you some equations about VE and VB. So VE is the node voltage at the emitter, which is the product of IE times RE. And remember, IE is the sum of IB and IC. So how should the value of IB be known? For example, I just said to you that VE is IE times RE, and IE is IB plus IC. Now I know IC is 2 milliampere, but I don't know IB, but I can have the value of IB because I just showed the beta value. So IB is IC over beta. So 2 milliampere divided by 200 will be the value of IB. So let me compute that, how much is the value. So IB comes out to be, so it's come out to be 10 microampere, right? And therefore your IE would be 10 microampere plus 2 milliampere. And that value is, we have to compute now. That comes to be, that is 2.01 milliampere. So I is known. With that value, we can multiply the value of IE with this RE actually to get the value of VE. So it would be, VE would be 2.01 milliamp multiplied by 750 ohm. That comes out to be 1.5 volts approximately. Okay, so VE is known. So obviously, if you know the voltage here VE, then VB would be VE plus VBE. This is your VBE. So let's write VB will be equal to 1.5 plus 0.7, which is about 2.2 volt. Now I know the value of VB, I know the value of VE, all these things. Now I go to get the value of resistors R1 and R2. So I got the base current value. I know the value of base current. I know the value of emitter current. I know the value of collector current. I know the value of RC and RE. Now the next step is to get the values of R1 and R2. For that, I need to do some arrangement. So let me clean all this drawing here and let me see how I can choose this. Right. So what I need to do, I would need to apply the Thevenin's theorem to the circuit right here to get the value of R1 and R2. Okay, these are two unknowns. So earlier circuit is this one. This is my circuit. And if I apply a Thevenin's equivalent to this circuit, so this is connected to the ground actually. No, this is not connected to the ground. Let me just be clear with that. So I need to get the value of R1 and R2. So I convert this circuit into the circuit as shown in this slide right here. So this is my circuit right here. So what I see, this is my transistor and I have this voltage VB, voltage VE, and I say there is this voltage VTH, Thevenin's equivalent. So Thevenin's equivalent is given as VCC multiplied by R2 divided by R1 plus R2. So it just the formula I have applied. So this is it. And then RTH is the parallel combination of R1 in parallel with R2. So I'm actually converting this circuit into this circuit. Okay. So by applying the Thevenin's. So with that, I got these two equations, the value of VTH and the RTH. Now there are two things to understand here. So one is the value of the input resistance RIN at DC, which is given in the specification, that is 4 kilo ohm. I know that. And then there is second resistance, that is the resistance we get by looking into the base at the DC, that is called as RIB. And the values of those two resistances are given by this formula. Ri in DC is the parallel combination of Thevenin's equivalent RTH right here in parallel with the resistance RIB. Okay. And then RIB DC is given as 1 plus beta. Remember, beta we just saw from the SPICE model is 200 and small re plus capital RE, where small re is the ratio of voltage over current, that is Ohm's law, where VT is the thermal voltage 25 millivolt divided by IE is approximately 2.01 2.01 milliampere, not 2.01, exactly 2.01 milliamp. And that comes out to be 12.4, let's say 12.4 ohm. Okay. So now with these values in mind, we move to next step. So right. So let me just clean this drawings here. So what I see here, I computed the value of RIB with the formulas. That comes out to be 138 ohm, and this is that resistance. So very low impedance into the base. And then using that, I solved for Thevenin's equivalent resistance RTH, which gives me according to this formula, the value of RTH is 4 kilo ohm. And then using RTH and the VTH, I have the values of these two resistors. R1 is about 53 kilo ohm and R2 is 4 kilo ohm. So how about I go back to my schematic and set those values. So 53 and 4 kilo ohms. So here I am. I will set those value. Here it is my 53 kilo ohm, and then this is my 4k ohm. That's it. So I am getting those values there. Back to my discussion here. Well, let me just get them here. What we have done here, we are actually sharing this to so we are done with the value of resistor. We have chosen the transistors. So you now see that with all values set, we are going to run our first analysis .op, and as I explained in the theory, you need to remove the all capacitances from the circuit, the load resistance also taken out, and input small signal AC source has been also removed, or in other words, say it is set to 0. Now, with the DC voltage set to 30 volt, resistor RC 7.5K, RE is set, transistor is set, and here is your output voltage that we need to see the different currents and the voltage values. So what we are going to do, we'll run the simulation with the .op analysis. So we'll check all resistor currents and the voltages. So here, output voltage is 16 volt, what we predicted. Theoretically, we calculated it half the supply voltage, that is 15 volt, and it is simulation is 16, so pretty close. Then the voltage at the base, which is here, is 2 volt. Voltage at the node 0002, it is this node, that is the voltage at the emitter terminal, which is like 1.4 volt. So it is VB minus VBE would be 1.4 volt. This is the node voltage at 001, which is the this voltage supply rail. The collector current is 1.8 milliampere. The base current is 8.2 microampere, pretty close values to what we calculated in theory. And this is also 1.87 emitter current milliampere. And then you have the current through the resistor RC, which is a collector current, and the current through the R1 and R2 comes out to be 0.5 milliampere each. Now we are done with the DC operating point, so it is most likely that this circuit will work as expected. We are going to apply a small signal voltage source here for amplification, and we are expecting amplified output here. We'll see how much is the gain. Gain is basically 10, that is set by the values of the resistor. We'll see that how much the gain will add. Now, next step is to incorporate, bring back the all the sources, that is the AC sources and the capacitances that we removed from the circuit. So let us bring them back one by one. So what I'll do here is go back to component library, click here voltage, and I will place that voltage source right over here, and then press escape button, then click ground right here, that voltage source here. Then I need a capacitors, then I will see CAP capacitor comes here. Then I want to press Control R from this, and then one capacitor here, one capacitance here, and control R will rotate one capacitance here. Then I need a resistor also, which is 1K. Remember, we have the value of this resistor 1 kilo ohm. So I will take that value, and then it's time to make the connections. RL goes here, and then this guy goes here, maybe little here, and then we close this. The capacitor is connected. The capacitor one terminal here. This capacitor goes here, and we make those connections right here and here, all these things. Now the value of the capacitance is, let us set to be 1 microfarad. We just want to make sure that these capacitances are high enough so that at the signal frequency of 10 kilohertz, which is our input signal, they acts as a short and they let the signal pass through that. Then this is like one. Their impedances or reactances should act as a short at the desired operating frequency. And this was about, let's say, uh, the reactance. So it's like again 1 micro. We'll see the impact of these capacitances. Now, with the capacitor value set, let's click the advanced, choose a sinusoidal voltage source. Here we set DC offset 0. Then amplitude is 10 milli, what we want. Frequency is 10 kilohertz, what we discuss. And then let's say you have 10 cycles you want to run. This sine wave source has been set up in a particular way. Put it here. Now in the bottom, you see with that operating point, after that we have set two regular analysis. We are going to see these two. So first, let me enable the transient analysis. So right click here. After right click, I see for the transient analysis, I will enable this analysis. So dot tran, I'm running it from 0 to 10 millisecond, and start time is 0 seconds at the step of 1 millisecond. So that's the syntax. Once that is done, I will just click run, and let me close the other two extra parameters of the circuit. So now I am done with this circuit. I will click run, and here I have to close these graphs because I don't have those graphs in my circuit. So close them right here. Okay, they keep coming here. So I don't have that right here. And let me clear the drawing. And then here also. Now this is my output actually. And on the upper graph part of the graph, I want to add the trace. Will plot the input signal. So voltage at the node. So I can't see the nets here because I haven't labeled them. So why not just click on the schematic and have the probe help me do that. So now you got to see that I have this beautiful waveforms. I'm going to zoom on the portions. Let me just zoom those waveforms, and here I see that the input is from 0 to 10 millivolt peak or 20 millivolt peak to peak, and the output is inverted, like going to 4 uh 400 something. So it's like the amplification. Let me just see how much is the peak. It's about zoom to fit. Yeah, it's about like let's right click here. Um, Top is 450, bottom is this one, and tick is 90. So how about I just do it like 10 millivolt and see if things are happening. or maybe just have them on together. So now it is what? Yeah, it's about 400 millivolt, right? So output is 40 times greater as expected. Theoretically, we had the gain of 50. Remember, in this one, we had the gain, which was set by ratio of RC divided by RE, and this is 50, and this more than 50. This is in theory, and AV is approximately 45, so simulations, and that's correct, and it is really having that one, right? Now you have to see a little bit difference here, that the output waveform is little bit tilted, is like not exactly a pure sine wave, but that is most likely due to the values of the capacitors we have chosen. So here we are done with the amplification. So let me play with the value of the bypass capacitor. If I increase it to, let's say, 10 micron and simulate the waveform again, now you see I have a better waveform at the output, and I'm approaching the gain of 50. So 10 millivolt peak, 500 millivolt peak. So that's the 50 times amplification I am having. So wonderfully well, I am able to simulate the response of the amplifier in a time domain, and other things also I can check. So perfect design of the common emitter amplifier using the transistor and the values chosen. Theory and simulation results are a pretty close match. You can have other voltages plots here. For example, add plot pane, and maybe here I want to plot the voltage at the base. So here I click here, and that's the voltage at the base. So everything is varying around the operating points. So that is the Q point. All the currents and voltages will vary. Now the next job is to simulate the DC response. The DC response has been done. Time domain response has been done. Next step is to simulate for the AC response that we are going to do in the next part. So till then, stay tuned. Hope you like this video.